Welcome. Find a comfortable position now. Let your body settle into whatever is beneath you. Feel the weight of your limbs. Let your shoulders drop. Tonight, we are going to drift slowly through the stars. We will visit the places where stars are born, where they live out their long, quiet lives, and where they finally fade away. You don't need to remember any of this. You don't need to follow closely. Just let the words wash over you like a warm, slow current. If your mind wanders, that is perfectly fine. Let it wander. The story will carry on gently beside you. Take one slow breath in and let it go. Again and once more. Good. You are ready. Let's begin. Somewhere deep inside every star, something remarkable is happening. Stars are not just burning, they are building. Right now, in the core of our sun, hydrogen atoms are being pressed together with such enormous force that they merge and become helium. This process is called nuclear fusion, and it is the reason stars shine. But that is only the beginning of the story. As a star grows older and its hydrogen begins to run low, it starts fusing heavier things. Helium becomes carbon. Carbon leads to nitrogen, then oxygen. In the most massive stars, the ones far larger than our Sun, the process goes further still. Silicon, sulfur, and eventually iron are formed deep in the core, under pressures and temperatures almost impossible to imagine. Think of a star as a factory running through a long series of shifts. Each shift produces something new. Each new element requires more heat, more pressure, more energy than the last. And then, when the fuel finally runs out, when a massive star reaches the end of its long life, something extraordinary happens. It explodes. A supernova is one of the most violent events in the universe. In a matter of seconds, an entire star tears itself apart and flings everything it has ever made out into the surrounding space. All those elements, carbon, oxygen, iron, calcium, scatter into the darkness between the stars. Over millions of years, that scattered material drifts and gathers. It mixes with clouds of gas, and slowly, new stars form. New planets form. And on at least one of those planets, life forms. The iron in your blood right now was made inside a star that died long before our sun was born. The calcium in your bones came from the same kind of process. Every element in your body, heavier than hydrogen and helium, was forged in a stellar core and scattered by a stellar death. We are not just looking at the stars. In a very real sense, we are made of them. Let that settle quietly for a moment. Every star has a beginning. It starts in the dark. Somewhere in the galaxy, there is a vast cloud of gas and dust called a molecular cloud. It drifts slowly through space, cold and diffuse, barely visible. But inside it, something stirs. A nearby disturbance, perhaps a passing shock wave from a distant explosion, causes part of the cloud to ripple. Gravity takes hold. The gas begins to pull toward its own center, slowly at first, then faster. A clump of material grows denser. It heats up as it contracts. At first, it is just a warm core surrounded by a swirling envelope of gas and dust. This is called a protostar. It is not yet a true star. It is a beginning. Over hundreds of thousands of years, the protostar gathers more and more mass. The core grows hotter, the pressure builds, and then, when the temperature at the center reaches about 10 million degrees, something ignites. Nuclear fusion begins. The star has been born. From this point, the star settles into what astronomers call the main sequence. This is the long, stable middle of a star's life, where it fuses hydrogen into helium and shines steadily across space. Our Sun has been in this phase for about 4.5 billion years, and it has roughly another 5 billion years to go. How long a star stays on the main sequence depends almost entirely on how massive it is. A star much larger than the Sun burns through its fuel in just a few million years, blazing intensely and dying young. A small red dwarf star, just a fraction of the Sun's mass, can burn so slowly and so efficiently that it could last for trillions of years, far longer than the current age of the universe. After the main sequence, the paths diverge. A star like our Sun will swell into a red giant, shed its outer layers gently into space, and leave behind a small, glowing core. A heavier star will end far more dramatically, expanding into a supergiant and finally detonating in a supernova, leaving behind something strange and dense, a neutron star, or perhaps a black hole. Each path is different. Each ending feeds back into the beginning of something new. Imagine you are an astronomer in the early 1900s. You have spent years collecting measurements of stars, their brightness, their temperatures, their colors. And you begin to notice something. When you plot all of these stars on a simple graph, with temperature along one axis and brightness along the other, they don't scatter randomly. They form patterns. Two scientists working independently, Einar Hertzsprung and Henry Norris Russell, made this discovery around the same time. The graph they created is now called the Hertzsprung-Russell diagram, or simply the HR diagram, and it remains one of the most important tools in all of stellar astronomy. Most stars, including our Sun, fall along a broad diagonal band running from the upper left of the diagram to the lower right. This band is called the main sequence. Stars in the upper left are hot, massive, and incredibly bright. Stars in the lower right are cool, small, and dim. But not all stars sit on this band. In the upper right corner of the diagram, you find the giants and supergiants. These are stars that have evolved beyond the main sequence. They are large and cool, glowing with a reddish light despite being among the most luminous objects in the sky. In the lower left corner, you find the white dwarfs. These are the remnants of smaller stars, incredibly dense, slowly cooling. They are faint but very hot. What makes the HR diagram so powerful is that it reveals the entire sweep of stellar evolution in one simple picture. You can look at where a star sits on the diagram and understand something about where it is in its life. A star's position is not random. It tells a story. Astronomers today still use this same diagram, updated with data from thousands and thousands of stars. It remains a cornerstone of how we understand the sky above us. Here is a simple truth about stars. The more massive a star is, the more dramatically it lives, and the sooner it dies. Mass is the single most important property of any star. It determines how bright a star shines, how hot its surface is, how long it survives, and what it leaves behind when it is gone. The relationship between mass and brightness is striking. A star with 10 times the mass of our Sun is not 10 times brighter. It is roughly 10,000 times brighter. The extra mass creates far greater pressure in the core, which drives nuclear fusion at a far greater rate. But that comes at a cost. A star burning 10,000 times as brightly as our Sun is using up its fuel 10,000 times as fast. Our Sun has enough hydrogen to last about 10 billion years in total. A star 10 times more massive might exhaust its fuel in just a few tens of millions of years. In cosmic terms, that is very brief indeed. At the other end of the scale, a red dwarf star with perhaps 1/10 the mass of our Sun burns so slowly and so carefully that its hydrogen could last for trillions of years. These small stars are quiet and steady, outlasting virtually everything else in the universe. Mass also determines what happens at the end. Stars with less than about 8 times the mass of the Sun end their lives relatively gently. They swell, shed their outer layers, and leave behind a white dwarf. Stars more massive than that follow a very different path. Their cores collapse suddenly and violently, triggering a supernova. What remains is either a neutron star or a black hole. In this sense, a star's mass is its destiny, set at birth, shaping every moment that follows. How do we know how far away a star is? It is not as though we can stretch a measuring tape across space. And yet, astronomers can measure distances to stars with remarkable precision, using a method so elegant it requires nothing more than careful observation and simple geometry. The technique is called stellar parallax. Hold your finger up in front of your face. Close one eye, then open it and close the other. Your finger seems to jump slightly against the background behind it. That apparent shift is parallax, caused by looking at the same object from two different positions. Astronomers do exactly the same thing, but with the Earth as the shifting viewpoint. Because the Earth orbits the Sun, it is in one position in January and the opposite position in July, about 300 million kilometers away from where it started. By photographing a nearby star in January and again in July, and measuring how much it appears to shift against the distant background stars, astronomers can calculate its distance using trigonometry. The unit used for this kind of measurement is called a parsec. 1 parsec is the distance at which a star would show a parallax shift of exactly 1 arcsecond, which is a tiny, tiny angle. 1 parsec equals about 3.26 light years, or around 31 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 1.3 parsecs away. The limitation of stellar parallax is distance. For stars more than a few thousand light-years away, the apparent shift becomes too small to measure accurately from the ground. But space telescopes have changed this. The Gaia telescope, launched by the European Space Agency, has measured precise parallax distances for over 1 billion stars across the Milky Way, building the most detailed three-dimensional map of our galaxy ever made. All from watching stars appear to shift ever so slightly against the background of space. When starlight passes through the right kind of instrument, it spreads apart into a rainbow of colors. But if you look carefully at that rainbow, you notice something. Dark lines crossing through it at specific places. These lines are not random. Each one corresponds to a precise wavelength of light that has been absorbed by a specific element in the star's outer atmosphere. This is stellar spectroscopy, and it is one of the most powerful tools astronomers have ever developed. Every chemical element has its own unique pattern of absorption lines, like a fingerprint. Hydrogen absorbs light at certain wavelengths, helium at different ones, iron, calcium, sodium, oxygen. Each leaves its own distinct mark in the spectrum. By reading these dark lines, astronomers can tell exactly which elements are present in a star, and in roughly what quantities. But the information hidden in starlight goes even further. The width and intensity of each line reveals details about the temperature and pressure in the star's atmosphere. A broader line might indicate higher pressure. A stronger line might point to a greater abundance of that element. And then there is the Doppler effect. If a star is moving toward us, the lines in its spectrum shift slightly toward the blue end. If it is moving away, they shift toward the red. By measuring this shift, astronomers can calculate exactly how fast a star is moving relative to Earth and in which direction. All of this from a beam of light split into colors. Spectroscopy is the reason we know the composition of stars millions of light years away without ever visiting them. It turns starlight from something beautiful into something deeply readable. Most stars do not live alone. Our Sun is something of an exception, drifting through space without a companion. But across the galaxy, more than half of all stars exist in pairs or small groups, bound together by gravity, orbiting each other in a slow and endless dance. These are called binary and multiple star systems. Some binary pairs are close enough that they complete an orbit in just hours. Others are so widely separated that a single orbit takes thousands of years. In some systems, both stars are visible through a telescope, and astronomers can watch them slowly circle each other. These are called visual binaries. Others are too close to resolve individually, but betray themselves through the Doppler shift of their spectral lines. As one star moves toward us and the other moves away, the lines in their combined spectrum split and shift back and forth. These are spectroscopic binaries. And then there are eclipsing binaries, where the orbit happens to be aligned such that the stars periodically pass in front of one another from our point of view. When one star blocks the other, the total brightness we observe dips predictably. These dips in brightness are a window into the geometry and size of each star. Binary systems matter enormously to astrophysics because they allow astronomers to measure something very difficult to determine otherwise: stellar mass. By applying Newton's laws of gravity to the observed orbits, the masses of both stars can be calculated directly. Multiple star systems with 3 or more stars add further complexity. Gravitational interactions between the stars can alter orbits over long timescales, sometimes dramatically. And when stars in a close binary exchange mass, it can change the entire course of their evolution. These systems are not just beautiful, they are laboratories. Stars carry invisible forces within them. Deep beneath the surface of our Sun and countless other stars, electrically charged particles are in constant motion, rising and falling in great churning columns of hot plasma. This movement, combined with the star's rotation, generates magnetic fields. The process is called the dynamo mechanism. It works in a star the way a generator works here on Earth, turning movement into magnetism. On the Sun's surface, the effects of this magnetism are visible. Sunspots are the most obvious sign. They appear as darker patches on the solar surface, regions where intense magnetic fields suppress the normal flow of heat from below. Because they are slightly cooler than the surrounding surface, they appear dark by contrast. The Sun's magnetic activity doesn't stay quietly contained. Sometimes a sudden release of magnetic energy produces a solar flare, a burst of radiation streaming out across the solar system. Other times, enormous clouds of plasma erupt from the corona in what are called coronal mass ejections. When these clouds reach Earth, they can disturb our planet's own magnetic field, triggering auroras and, in extreme cases, disrupting satellites and power grids. Younger stars rotate faster and, as a result, tend to have stronger magnetic fields and more frequent eruptions. As stars age and slow their rotation, their magnetic activity generally quiets. This matters beyond the star itself. A star's magnetic field shapes its wind, the stream of particles flowing outward through its surrounding space. For planets orbiting close to an active star, this can have significant consequences for the atmosphere and potentially for the conditions needed for life. Stellar magnetism is quiet, invisible, and yet it reaches across vast distances. Picture a single sugar cube, something small enough to hold between two fingers, something that weighs just a few grams. Now, imagine that same volume of material packed so tightly that it weighs 1 billion tons. This is the density of a neutron star. Neutron stars are what remain after a massive star explodes in a supernova. The outer layers of the star are blasted away, but the core collapses inward with tremendous force. Electrons and protons are crushed together to form neutrons, and the collapse continues until the neutrons themselves resist any further compression. What remains is a sphere, perhaps 10 kilometers across, but containing between 1 and 2 times the mass of our entire Sun. 10 kilometers. You could drive across a neutron star in about 6 minutes. Some neutron stars spin very rapidly and emit beams of radio waves or other radiation from their magnetic poles. As the star rotates, these beams sweep through space like the beam from a lighthouse. If one of those beams happens to point toward Earth, we receive a regular pulse of radiation with each rotation. These are called pulsars. Some pulsars rotate hundreds of times per second with extraordinary precision. Their pulses arrive so regularly that they can be used as cosmic clocks, accurate enough to test the predictions of Einstein's general theory of relativity. Astronomers have also used pulsars to hunt for gravitational waves, ripples in the fabric of space-time predicted by Einstein and now confirmed. Neutron stars exist at the very edge of what matter can be. They push the laws of physics to their limits, and in doing so, they give us a way to test those laws under conditions we could never replicate in any laboratory on Earth. Stars need somewhere to be born. That somewhere is a nebula. Nebulae are vast clouds of gas and dust scattered throughout the galaxy. Some are so large that it would take light thousands of years to cross from one side to the other. They are the raw material of the universe, the reservoirs from which new stars are drawn. Within a nebula, the coldest and densest regions are called molecular clouds. These are places where hydrogen exists not as individual atoms, but as molecules bound in pairs. Here, the temperature can drop to just a few degrees above absolute zero. Here, gravity slowly gains the upper hand. When something disturbs a molecular cloud, a shock wave from a nearby supernova perhaps, or the gravitational pull of a passing object, parts of it begin to collapse. The gas pulls inward, falls toward the center, heats up. A protostar begins to form. This process rarely produces just one star. Molecular clouds fragment as they collapse, forming dozens or hundreds of protostars at the same time. This is why stars so often form in clusters. As the young stars ignite, they push back against the cloud around them. Stellar winds and radiation pressure blast outward, sculpting the nebula into spectacular shapes. Sometimes this pressure compresses nearby pockets of gas, triggering even more star formation. Sometimes it disperses the gas entirely, ending the cycle. The Orion Nebula is one of the most famous examples. A glowing cloud of gas visible to the naked eye. Inside it, right now, new stars are being born. Some may one day have planets. Some of those planets may one day hold the conditions for life. It all begins in the quiet dark of a nebula. When a star like our Sun reaches old age, it does not simply fade away. It swells. As the hydrogen in its core is exhausted, the delicate balance between gravity and the pressure of fusion begins to shift. The core contracts and heats up, while the outer layers expand outward, growing enormously. The star's surface cools as it spreads, and the star takes on a reddish color. It has become a red giant. A red giant can grow to tens or even hundreds of times the diameter of the original star. When our Sun reaches this stage in about 5 billion years, it will likely expand far enough to engulf Mercury and Venus, and possibly reach the orbit of Earth. Arcturus, one of the brightest stars in the night sky, is a red giant. It glows with a warm orange-red light and is roughly 25 times wider than the Sun. For stars much more massive than the Sun, the expansion goes further. These stars become supergiants, the largest stars in the known universe. Betelgeuse, the bright reddish star in the constellation Orion, is a supergiant so large that if it replaced our Sun, it would extend beyond the orbit of Jupiter. Supergiants are not just large, they are complex. Their cores continue fusing heavier and heavier elements, moving through carbon, oxygen, neon, magnesium, silicon, building layers like an onion until the core is made of iron. And when the core is iron, fusion can no longer continue. The end is near. Both red giants and supergiants shed material into space as they age, enriching the galaxy with the elements they have spent their lives creating. When they die, they return everything they have made to the interstellar medium, and the cycle continues. After all the burning is done, after the outer layers have drifted away, what is left? For a star like our Sun, what remains is called a white dwarf. A white dwarf is the exposed core of a former star. It has roughly the mass of the Sun, but compressed into a sphere about the size of Earth. It is extraordinarily dense. A single teaspoon of white dwarf material would weigh several tons. But it is no longer fusing anything. The nuclear fires have gone out. What keeps a white dwarf from collapsing further is not fusion, but something called electron degeneracy pressure. The electrons inside the star resist being squeezed any closer together, and this resistance holds the star up against gravity. With no energy source, a white dwarf simply radiates the heat it already has. Slowly, over billions of years, it cools from white to yellow, and eventually, after an almost incomprehensibly long time, it would cool to become a cold, dark remnant. Though no white dwarf in the universe is old enough for this to have happened yet. Most white dwarfs are composed primarily of carbon and oxygen, the ashes of the helium fusion that powered the star's final active phase. Sometimes, in a binary system, a white dwarf will begin pulling material from its companion star. This stolen material builds up on the surface until it ignites in a sudden burst of fusion, a nova. If enough material accumulates, the entire white dwarf can detonate in a catastrophic explosion called a Type 1a supernova. These explosions are so consistent in their brightness that astronomers use them as cosmic measuring sticks, standard candles to measure vast distances across the universe. Even in death, stars find ways to be useful. Not every collapsing cloud of gas becomes a true star. Some fall just short. These objects are called brown dwarfs, and they occupy an unusual place in the universe. Too large to be a planet, too small to be a star. A brown dwarf forms the same way as a star, through the gravitational collapse of a cloud of gas and dust. But it never gathers quite enough mass to sustain full hydrogen fusion in its core. The threshold is roughly 13 times the mass of Jupiter. Objects below that threshold cannot ignite sustained nuclear burning. And yet, brown dwarfs are not entirely inert. In their early years, many brown dwarfs can fuse deuterium, a heavier form of hydrogen. This requires much lower temperatures and pressures than ordinary hydrogen fusion, and it does not last long. Eventually, Even this faint nuclear warmth fades, and the brown dwarf slowly cools and dims. Because they emit most of their light in the infrared, brown dwarfs are very difficult to detect. They appear faint and cold against the darkness of space, and for a long time astronomers were not sure how common they were. We now know they are quite common indeed. Brown dwarfs matter to astrophysics for several reasons. They help fill in our understanding of how mass is distributed in the universe. They serve as a natural bridge between the largest planets and the smallest stars, helping us understand both kinds of objects better. And in star clusters, where they exist in significant numbers, they contribute to the overall mass and gravitational behavior of the cluster. They are the quiet ones, the ones that never quite made it to the light. At the far end of stellar mass, among the most extreme stars in the galaxy, you find objects that seem to push against the very idea of stability. Two kinds of stars stand out in particular. The first are called luminous blue variables, or LBVs. These are enormous stars, among the most massive in the universe, and they are deeply unstable. They go through periods of intense activity, sometimes ejecting vast quantities of their own mass into the surrounding space in great eruptions. Their brightness can change dramatically over years or decades. The most famous example is Eta Carini, a star in our own galaxy that underwent a tremendous outburst in the 1840s, becoming briefly the second brightest star in the sky. It expelled material that formed a double-lobed nebula around it, still visible today. Astronomers believe Eta Carini may one day explode as a supernova, though predicting exactly when is beyond our current ability. The second kind are called Wolf-Rayet stars. These represent a later stage of massive star evolution. Their powerful stellar winds blow so strongly that they strip away the outer layers of the star entirely, exposing the intensely hot interior. Their spectra are distinctive, showing broad, bright emission lines rather than the dark absorption lines seen in most stars. Wolf-Rayet stars are shedding mass at tremendous rates, enriching the surrounding interstellar medium with heavy elements. They are thought to be the predecessors of certain types of supernovae, and possibly of some of the most energetic explosions in the universe. Long-duration gamma-ray bursts. Both kinds of stars live fast, lose mass dramatically, and die violently. They are among the most spectacular objects in the sky. Stars rarely prefer to be entirely alone. Across the galaxy, many stars are gathered together in groups called star clusters, born from the same cloud of gas and dust, bound together by their shared gravity. There are two main kinds. Open clusters are loose collections of stars, usually a few hundred to a few thousand of them, found scattered through the flat disk of the Milky Way. They tend to be young, containing stars that formed relatively recently. The Pleiades, that tight little cluster of blue-white stars visible on a clear winter night, is an open cluster, about 100 million years old. Over time, open clusters gradually come apart. Gravitational encounters with other stars and clouds of gas slowly strip away their members. After hundreds of millions of years, the stars disperse into the general population of the galaxy. Globular clusters are something very different. These are ancient, compact spheres of stars, containing anywhere from tens of thousands to hundreds of thousands of members, packed densely together. They orbit in the halo of the galaxy, high above the galactic plane, and many of them are nearly as old as the universe itself. The stars in globular clusters formed early in the universe's history, when fewer heavy elements had yet been created. So they tend to be metal poor, made mostly of hydrogen and helium, offering astronomers a window into the early conditions of the cosmos. Both kinds of clusters serve as laboratories. All the stars in a cluster formed at roughly the same time and from the same material, so differences between them reveal how mass alone shapes stellar evolution. They allow astronomers to test and refine our understanding of how stars live and age. Here is a question worth sitting with gently. What if dark matter, the invisible substance that makes up most of the mass in the universe, played a direct role not just in shaping galaxies, but in powering the very first stars? This is the idea behind the dark star hypothesis. In the very early universe, before the first true stars formed, dark matter was distributed differently than it is now. There were regions where it was exceptionally dense, and some physicists have proposed that in those regions, something unusual may have happened. A leading candidate for dark matter is a type of particle called a WIMP, a weakly interacting massive particle. When two WIMPs meet, they can annihilate each other, releasing energy in the process. In a region dense enough with dark matter, this annihilation could produce enough energy to heat a large cloud of gas and prevent it from collapsing further, holding it in a kind of bloated, warm equilibrium. The resulting object, a dark star, would be very different from ordinary stars. Much larger, much cooler, glowing primarily in the infrared rather than invisible light. No dark star has ever been observed. They exist so far only in theory, but the hypothesis is genuine and is taken seriously by researchers. If dark stars existed, they would have been among the first objects to light up the universe, and they would have had enormous mass, perhaps hundreds of thousands of times the mass of our Sun. Proving or disproving the hypothesis may require new discoveries both in particle physics and astronomy, but it represents something important: the idea that dark matter may not be merely a passive backdrop. It may have actively shaped the earliest chapter of stellar history. The stars in our galaxy are not spread evenly through space. Some places are crowded, some are nearly empty. The central bulge of the Milky Way, the dense, rounded core at the heart of the galaxy, is packed with stars. Here, gravity has concentrated ancient stellar populations into a brilliant, compressed mass. The night sky from a planet near the galactic center would be ablaze with stars. Moving outward, the spiral arms of the galaxy carry their own dense regions. These arms are rich in gas and dust, the ingredients for star formation. New stars are born here, clusters ignite, and the arms glow with blue-white young stars. Our Sun sits in one of these spiral arms in a relatively quiet suburban region of the galaxy. Further out still, and above and below the galactic plane, is the halo. This vast spherical region contains relatively few stars, and those it does contain are old. They travel in slow elliptical orbits around the galaxy's center, often gathered into those ancient globular clusters we touched on earlier. The way stars are distributed through the galaxy shapes how the galaxy behaves. Dense regions have higher rates of gravitational encounters between stars. This can alter orbits, trigger star formation, and, in extreme cases, near the galactic center, stars can be flung outward at tremendous speeds. Understanding where stars are and why helps astronomers trace the history of the Milky Way, how it formed, how it has evolved, and what role dark matter plays in holding it all together. The galaxy is not a static picture. It is a slow-turning, living system, and the distribution of its stars is one of the most important clues to how that system works. In the early 20th century, a young woman named Henrietta Swan Leavitt was working at the Harvard College Observatory. Her task was to study photographic plates of the sky, cataloging the brightness of stars. She began to notice something in a particular type of star called a Cepheid variable. Cepheid stars pulsate. They expand and contract in a regular rhythm, growing brighter, then dimmer, then brighter again. What Leavitt discovered was a precise relationship. The longer a Cepheid's pulsation period, the more luminous it truly was. This relationship, now called the Leavitt law or the period luminosity relationship, became one of the most important tools in astronomy. Here is why. If you observe a Cepheid variable and measure how long its cycle takes, you can determine how luminous it actually is, how bright it would appear if you were standing at a standard distance from it. Then you can compare that to how bright it actually appears in the sky. The dimmer it appears compared to what it should be, the farther away it must be. It is a cosmic ruler. In the 1920s, Edwin Hubble used Cepheid variables to measure the distance to a fuzzy patch of sky called the Andromeda Nebula. The distance he found was staggering. It was not a nebula within our own galaxy. It was an entirely separate galaxy, one of billions. And then Hubble went further. By measuring the distances to many galaxies using Cepheids, he discovered that the more distant a galaxy was, the faster it was moving away from us. The universe was expanding. All of that from the quiet blinking of pulsating stars, mapped onto photographic plates by a woman working methodically at her desk. Within star clusters, there is a mystery. Scattered among the older, cooler stars that you would expect to find in an ancient globular cluster, there are occasionally stars that don't belong. They are brighter, hotter, bluer. They look like young stars, but the cluster is old. All of its stars should have aged together. These out-of-place objects are called blue straggler stars. How do they exist in a place where no young stars should be? Astronomers have two leading explanations. The first is collision. In the densely packed heart of a globular cluster, stars are close enough together that direct collisions can occur over astronomical timescales. When two stars merge, they combine their masses into a single, larger star. This new star has more hydrogen fuel available, and it sits higher on the main sequence, appearing younger and hotter than its neighbors. The second explanation is mass transfer in binary systems. If two stars are in a close orbit, one star can pull material from the other. The star gaining mass is effectively rejuvenated. Its evolutionary clock is reset. Either way, the blue straggler appears younger than it has any right to be. These stars are a reminder that stellar evolution is not always a solitary journey. Stars in clusters interact, influence each other, sometimes transform each other entirely. The simple picture of a star being born, living, and dying alone gives way to something more complicated and more interesting. And perhaps that is a good place to come to rest tonight. The universe is complicated and interesting. Stars are born in clouds, live in clusters, exchange mass with neighbors, explode, collapse, scatter their elements across space, and begin again. You are part of that long story. Let your breathing slow now. Let the stars continue their quiet work far above you. You can drift gently all the way into sleep.